Thank you. Well, hello everyone. In this presentation, I will speak about TauREx2D, which is a version of TauREx which performs atmospheric retrievals using two-dimensional forward models. Usually, when we study exoplanetary atmospheres, we are in this geometrical configuration where we have an observer here. We have the star, this red ball that you can see here, and we have a planet transiting in front of the star. Using spectroscopic information with this geometrical configuration, we can extract many information on the atmospheric properties of the exoplanets. The fact is that using Bayesian frameworks, if we want them to converge in a reasonable amount of time, we need to simplify the atmospheric model as much as we can. Indeed, usually, if we want to perform a fully consistent GCM model, Bayesian frameworks would not really converge in a matter of months or weeks or months. It will not, well, it's also possible that we will not even converge. So sometimes what we do is to simplify the atmosphere using a plane parallel one-dimensional approximation. So we reduce sometimes the three-dimensional structure of the planets to a one-dimensional models. In this case, we can quickly perform millions of different atmospheric models, and we are able to plug them into a Bayesian framework to make it converge indeed in a reasonable amount of time. The fact is that for this one-dimensional approximation can work for some classes of planets, but we still don't need to forget that planets are can be very complex. They can have very complex three-dimensional structures, and sometimes a one-dimensional approximation can lead us to very biased understanding of exoplanetary atmospheres. And an extreme case could be the one of ultra Jupiters, in which we have a great dichotomy between the day side and the night side of the planets. In ultra Jupiters, we have an extremely hot and inflated day side compared to the night side. And the temperature in the day side could allow thermal dissociation for some of the molecular species. As you can see in this graph here, I display the thermal dissociation of species like H2 and H2O as a function of pressure and temperatures. So if we see water features, for example, in a transmission spectrum of a ultra Jupiter, we can be sure that that water belongs to some cold part of the atmosphere where water can remain at its molecular state, indeed. So when we perform atmospheric retrieval, we saw that sometimes 1D retrieval cannot really take into account these 3D effects, especially in ultra Jupiters. We have extreme cases, indeed. And at the same time, we cannot use still today with our tools fully consistent three-dimensional model within a Bayesian framework. So a good compromise would be to use two-dimensional models for the atmosphere, where we can describe an exoplanetary atmosphere using two dimensions. The radial dimension would allow us to discretize the atmosphere from the bottom to the top of the atmosphere. And the angular dimension, here parameterized by alpha star, allows us to discretize the atmosphere from the substellar to the antistellar point. So we divide the atmosphere into several cells with different pressure temperature values or pressure temperature profiles and different chemical compositions indeed. So if we perform a radiative transfer in such an atmosphere, we could get closer to a realistic case than the one performed using just a one-dimensional plane parallel atmosphere. So we implemented this geometry within TauREx, and we performed a few tests, retrieval tests. we used as a benchmark synthetic three-dimensional model of a planet like WASP-121b using GCM. We defined an atmosphere such as the substellar point was 3300 Kelvin, the antistellar point is 500, and we have an inner annulus of constant abundances at 2500 Kelvin. And then we put some chemistry in the atmosphere and we let it thermally dissociate according to the pressure and temperature values. Then we performed two realistic cases. To test TauREx2D, we put ourselves in the configuration when we don't have optical species covering the Rayleigh part, which gives us information on the radius of the planets, for example. And then we test the performances of TauREx2D in presence of optical species and then covering the Rayleigh part of the spectrum. Here we can see the final results in the case without optical species. We performed 2D retrieval, which gave us two statistically equivalent solutions. I will come to this later. And we also performed a one-dimensional retrieval, which also gave us a solution. And as you can see here, the residual are bigger than the one from the 2D retrieval. I will come also to this point later. If we look at the posterior distribution, unfortunately, I don't have the time to describe all of the details here, but if we see at the molecular abundances retrieved by TauREx2D compared to the ground truth represented by the red line, we see that TauREx2D went close to the expected solution indeed, and it found at the generate solution with two statistically equivalent solutions indeed. The same test has been performed in presence of optical absorbers using we perform different retrievals, 2D and 1D retrievals. And even here, the 2D retrieval gave a degenerate solution with two equivalent solution, a statistically equivalent solution, and we can see that it also converged around the ground truth of the model. But what's wrong, let's say, with 1D retrieval? What do we see with 1D retrieval? In the most complex case I shown you with optical species, we can see that the 1D retrieval returned let's say good-looking spectrum. It's a statistically valid spectrum, this one. And also the posterior distribution, they looked fine. They converged around the value. But as we can see here, we don't see any red lines. That means that actually we are totally biased towards a solution very far away from the ground truth. So when we perform 1D models, we can still find a statistically significant solution here, but it doesn't mean that we are retrieving parameters close to the ground truth of the atmosphere with observing. Usually when we perform retrieval, we should always compare different models. We can compare different models using computing, for example, the bias factor, which is the logarithmic bias factor. In this case is the logarithmic ratio between the Bayesian evidence of the two models. And here we can see that Bayesian and the logarithmic bias factor is higher than 40. That leads to a statistically significance of the two-dimensional model compared to the one-dimensional model higher than 5. It means that the 2D model here gives us a more reliable solution, so the 1D can be discarded. If this bias factor would have been 1, so the two models would have been equivalent, one should decide the simplest model just because of the Occam economic principle indeed. But in this case, the two-dimensional gave us a better solution, so it gave us, it should be the model to be chosen. So concluding, two-dimensional models are a good compromise between the model precision and the ground truth reality and the computational power. We saw how some classes of planets cannot really be represented by 1D models, like ultra Jupiters or planets which have a high asymmetry in their atmosphere. And when we compute and we perform atmospheric retrieval, we should always compare our models with other models, and the bias factor can help us doing this comparison. In this case, for the ultra Jupiters, the two-dimensional models always leads to a better solution and a preferable solution compared to the one-dimensional one. And yeah, TauREx2D can be downloaded from GitLab. It's also pip installable with pip install TauREx2D. And if you're interested, you can also see at the publication on astronomy and astrophysics. So that was my last slide. Thank you very much.
All right, thank you. Does anyone have any questions? They can raise their hand or type in the Slack chat. Well, if we don't have any right now,
looks like there's a hand up, Ted.
Can't see any hands. Can't see any. Oh, here, yes. All right, if you have your hand up, feel free to unmute.
Actually, no, I do not have any question. I could not lower my hand actually. Sorry.
All right. I have a question then. So what would be an example of a case where the 1D model might be just as good as the 2D model based on your bias factor?
For example, cold Jupiters could be a good case where we don't have an unbiased solutions. So all of the planets, for example, which don't show such a big dichotomy between the day side and the night side, could be good cases. But well, in any case, it strongly depends on the molecular distribution among the atmosphere. So if it does have big asymmetries in the distribution on the molecular species in the atmospheres, most cases the one-dimensional approximation will lead us to biases. It could be that we can perform a good statistically significant solution for that case, but it doesn't necessarily mean that we are retrieving the real parameter in the atmosphere. So they're very delicate tools. And so yeah, it could lead to a good, well, coming back to your answer, cold planets with a cold atmosphere could be good cases for the 1D approximation indeed.
Thank you.